Thank you for being here. This is your last talk of today, and your patience will be rewarded. So we have designed a security system that can offer fine-grained security control for large-scale storage systems, as that you can find in high-performance computing or HPC systems or cloud computing storage systems. This work was done in collaboration between the University of California, Santa Cruz and Sandia National Laboratories, who use a lot of HPC systems. So we're going to start with the problem we're trying to solve. Then I'll go over with the algorithm of Horus and its unique features that differs it from other security systems. The Horus algorithm is quite versatile and can be implemented in many different models. Here I will show you also our reference design that makes the best of the Horus algorithm. We will also evaluate our design and how it performs in various benchmarks. So Horus, we call the system Horus, who is an ancient Egyptian god of protection. And now he or she will protect our file system data. I don't know what. So Horus is designed to be a general purpose security system, and it's not intrinsically restricted to either supercomputers or cloud computer. But for this talk, we will mainly focus on the use of Horus with supercomputer or HPC systems. So why does HPC need better security? So this is a simplified HPC storage system model. So in the center, there's a shared file system that holds all the input, results, and checkpoint data, and thousands of computer nodes connected to this shared storage and do all the dirty work of data crunching. So in many HPC applications, this data can be confidential due to either national security or business concerns like this Monte Carlo simulation of business strategies or nuclear energy simulations or secret geographic data set. But currently, these data are mostly stored as plain text. So current HPC systems relies on a model called the perimeter defense. They have a hard exterior, but a soft interior. So they have a strong wall built around the system, a physical wall. So but little to no control within the system for either performance or management concerns. So since HPC systems can be very expensive to build, they're generally shared between projects. So on computer nodes, there may be many projects running in sequential. And also, these HPC applications run on computer nodes as super user, so they can easily steal the data from other tasks running on the same system. So this poses several problems. The first is that, as I said, a malicious program can steal the data from previous tasks running on the same computer nodes, and even worse, a malicious computer node that can see a rogue node here can steal all the data from all the tasks running on it. There are even more issues. Like besides information leakage, there are problems like malicious insider, a malicious system administrator, a bad guy from other projects running on the same machines, or even server room janitors can steal your data if this data is stored in plain text. And the second problem is for those people who lease storage or computing services like Amazon EC2, you have to fully trust these service providers to protect your data. And the third is that lacking security is hindering the adoption of some optimization technologies like the node local storage. So currently, most HPC computer nodes have no local storage. By adding some form of local storage, we can reduce the pressure on shared storage, or as the previous speaker talked about the active flash, we can do in situ analysis. However, without a proper protection, it makes it even easier by adding local storage for a malicious program to steal data from other projects. So encryption is a standard way of protecting confidential information, but for HPC applications with very large data set, key management remains non-trivial. So common practices use one key per file, or even one key for all the files, the whole data set. So clients who need to access encrypted files are given the corresponding keys to do their jobs. So for example, for the first computer nodes, if we wanted to process the file encrypted by using the red key, we will have to give it the red key. For those two computer nodes to process the file encrypted by using the blue key, we will have to give it the blue key to do their job. The problem here, if one client is hacked or accessed by a malicious program, the intruder will be able to get the file keys and access the whole file. So if this file data set is very large, we're leaking a large amount of information. So instead of giving a key that can access a whole file to client, we can encrypt the file by using unique keys for each file system block and give only the client the needed keys for performing their specific task. For example, here, these clients has only key 0 and key 1 to access the first 2 blocks of the file. Now, if this node is hacked or another program running on the same node steal the data, only the 2 blocks information will be leaked. But for a very large data set, which is very common in HPC, the key management overhead will be very high using this method. For example, for 1 terabyte of data, using an AES encryption with 256-bit key for every 4 kilobyte block, you will need to store and distribute and manage the keys of 8 gigabytes just in size. Just imagine keys of 8 gigabytes, that's horrible. So the Horus way to solve this problem. Horus is built based upon this 1 key per block mode, but Horus uses a keyed hash tree to generate block keys. A keyed hash tree is a simple tree structure, so each node in the tree is a key. Except for the root node, each node is a hash of its parent node, plus a positional parameter, like here the x concatenate y. So x here is a level of the tree, and y is a sequence number of nodes within that level. So we can actually use any keyed hash function here. So for example, giving any node, deriving a lower level key is easier. So here, giving kr, we call it the root key, we can easily derive key 00 by hashing kr plus 00. Similarly, with key 00, we can get key 11 very easily by hashing key 00 plus the positional parameter 11. But using a cryptographic strong hash function, getting a parent key or sibling keys from lower level keys is intractable. Intractable means it's computational hard. So with the keyed hash tree, we use nodes from the keyed hash tree as keys. So each file will have a unique root key R here, and given a preset keyed hash tree width and depth, we can generate the whole keyed hash tree here. So level by level, we reach the leaf level. So the leaf level keys will be used as block keys for encrypting file system blocks. As you can see, we call these leaf keys block keys because they are used to encrypt the file system block. And higher level keys called range keys because they cover a range of data blocks. So with keyed hash tree, having the region key enables a client to access a whole range of file system data blocks because the keyed hash tree generation is deterministic. Given key 00, any computer node can generate the key 20 to key 25 to decrypt the related file system data block. So the benefit is here. We can reduce the key management overhead if we want to give the computer node key 20 to key 25, instead of having to distribute and store 6 keys, we can just give it the key 00. The key distribution management overhead is reduced from 6 keys to just 1 key. And also, keyed hash tree enables Horus to provide fine-grained security control. If we want to give this computer nodes 2 more blocks from key 26, key 7, we just give it another range key, key 13. So with key 00 and key 13, the computer nodes can generate the keyed hash tree and get it from key 20 to key 27. And also on the server side, the key storage is also simplified by using keyed hash tree. So for example, instead of having to store 8 gigabytes of keys for 1 terabyte of data, we can just store this root key, and the whole keyed hash tree can be generated on the fly. The keyed hash tree can have different widths and depths for files of different sizes. So it can be wider and it can be deeper. So here, this keyed hash tree have a branching factor. We call it branching factor 2 because at each level there are 2 children. And the depth of the tree is 4. So next, as you can probably imagine, using a keyed hash tree to generate a large number of keys can be applied to practical systems in many different ways. Here we present the design we have used in our prototype system as a reference. It is designed for HPC storage systems. It has some unique, interesting features that can solve the issues I raised at the beginning of this talk. So this is a typical HPC system. It have these components, a metadata server, storage nodes working together to provide a shared storage service, computer nodes doing all the data crunching tasks, and I/O nodes help computer nodes to process I/O requests. This is only a simplified model. And the Horus design have three major components. The first is the key distribution server. Several servers working together can form a key distribution cluster. The second is Horus client libraries that run on computer nodes. We call them client. And the third part is the root keys of these files and range permission settings. They are stored in encrypted form in the shared file system. The central process of the design of Horus system is the key distribution process. It is a process of client request keys needed to perform their tasks. In our design, a key distribution process is carried out like this. So when a client sends a request to get the key 10 here, the key distribution server's job is to generate the upper part of the tree from the root key, get key 10, send it over the network to the client, and the client use key 10 to generate the lower part of the keyed hash tree, and calculate key 20 and key 21 to decrypt the corresponding data blocks. So the key component of Horus is a key distribution cluster. So our design have several interesting facts. The first is that the key distribution server is the only component that know the root keys of all files. The keys and range permissions are encrypted, like stored in a lockbox and stored in the shared file system. Only the key distribution server has the needed key to access these root keys protected in the lockbox. So by storing these keys encrypted in the shared file system, the key distribution server can be run without a local storage, so it can be stateless. So without having to handle the storage also makes this key distribution cluster very simple. So our prototype implementation have a multi-threaded implementation. It has only a few thousand lines of code, so it is very stable. It's very simple. So the good thing about being stateless is, the good thing about being simple is that it can be secure. So means the code base is simple, it can be rigorously tested and checked, so making it harder to hack than a storage or operating system which can have millions of lines of code. Also, the good thing of being stateless is it is scalable, because when you need more key distribution server, you can just throw in more servers, install the software. There's no need to consider about synchronization between nodes. So the scalability can be very good. Also, being simple and stateless means it is easy to deploy. So by our design, the key distribution server is located outside the HPC or cloud system, because when you are using an HPC or cloud service, generally you have no permission to modify the existing system. So by keeping the KDS outside the HPC or cloud service, you can just relieve the need to having to modify a current system or having to trust a service provider. So of course it's perfectly fine if you are the service provider or if you are the storage system vendor. If you want to incorporate the function of Horus into your system, actually it can provide better performance if the Horus functionality is done on the server side. But our design is that we want to solve the problems I raised at the beginning of the talk. So also we want the applications who use Horus to protect that data to be portable, so you can easily move the function of Horus from one system to another, and you can take the key distribution server along with you, especially for users using least computational hours from shared HPC or shared cloud services. So the client side of Horus, it can be implemented at various different levels. It can be done in the OS level for best performance compatibility with existing applications, but changing operating system kernel is very hard, as we have already seen in the morning, right? Thousands of bugs in the Linux file system after these many years. Also, the function of Horus can be implemented as a library or middleware, so we don't have to touch the operating system kernel, such as you can do it by using the fuse of Linux. In our prototype system, we implemented Horus as a library. So also the third option is for best application portability. It can be implemented right inside the application. So you can easily port your application from one HPC to another with no need to change either the operating system or library. So now I'm giving a brief introduction of how the key distribution process is done on a high level. The first step is computer node send requests to the key distribution server to request the range keys they needed. I assume here the job has already been properly dispatched to the computer node and it knows which range of the data needed for performing its task. So in our design, the KDS, key distribution server, have no local storage and have to request the root keys from the shared storage. The shared storage server returns the encrypted root key and file permission. Then the KDS uses the key it has to decrypt this data stored in lockbox and perform permission check whether this requesting computer has the right permission to access this data. And if it has, we calculate the upper part of the key hash tree to generate the range keys needed for this client. And then KDS will send the result keys back to the computer nodes. And the computer nodes with the proper range keys can calculate the lower part of the key hash tree to generate the block keys needed to perform its computational task. And as usual, the computer node can retrieve the encrypted data from the shared storage through the normal data access process. Then with the proper block keys and the encrypted data, it can decrypt the data blocks. The write process is similar to this process. It's described in detail in the paper. As you may have already discovered that this process doesn't handle authentication, and our paper doesn't cover authentication either. So Horus has to be used in combination with some proper authentication method, and all the steps I described will have to be done after proper authentication, and they have to be protected using techniques like SSL. So we have built a prototype system and evaluated the performance by using various benchmarks. The first we have done is analysis of key distribution performance because it's a core process. So the key distribution performance analysis will help us to understand how fast the keys can be distributed over the network, because it depends on the hash function, which hash function you use, and what kind of network you use. And the second is how many key distribution servers are needed if you want a certain IOPS or bandwidth. And it can also help us understand which step in this process is going to be the bottleneck. So we already knew that when a client requests a key from KDS, there are 3 time-consuming steps involved. This server-side calculation. The second is sending the key over the network. The third is the calculation on the client side. So with different settings, these 3 bars shows the different weight of this time-consuming process in the whole process. The prototype system we did use mainstream hardware. The key distribution server is multi-threaded. The hash function we chose is SHA-1 from OpenSSL, and you're actually free to choose whatever hash function you want. And the I/O library is MPI-IO. The encryption we use is AES 256 bits. And in the first benchmark, we want to saturate the KDS to see how it works under pressure. So we let the clients request all the leaf keys from the key distribution server. And by this design, all the keys have to be calculated on the server side and then distributed over the network to the client side. So the time will mainly be consumed by these 2 steps, the server-side key calculation and the network key transmission. The client here doesn't have to do any calculation work. So this is the results of the first benchmark. The x-axis is the number of client threads. The y-axis is 1,000 queries per second. With 1 KDS, we can achieve, as you can see, about 140,000 queries per second. This is somehow a good performance. And just for reference, a recent domain name server benchmark shows that a high-performance DNS server normally can only handle about 70,000 queries per second. So here, the key hash tree, we chose a very large depth, like depth equal 11, because we want to give the KDS the biggest pressure. So here you can see when there are more than 32 clients issuing requests, either the server or network becomes saturated because the performance never goes up. So in order to figure out which part is the bottleneck, we did the next benchmark. So we're still using 1 key distribution server. We removed the key hash function. We just commented it out. So we can now achieve about 278,000 queries per second, still one KDS. So this showed us that in previous benchmark, the bottleneck was hash function. So, and here we believe that 270,000 queries per second is actually how fast our network stack can distribute keys. So the next one, we use 2 key distribution servers. We achieved somehow similar 278,000 queries per second. Since 278 is just a shy of the double of 140. So this benchmark shows that KDS scales nearly linearly, which is very good. Since the KDS server-side calculation is CPU-bound, the performance highly depends on the speed of the hash function. What we use is SHA-1, and your mileage may vary, depends on what hash function you use. 140,000 queries per second is the speed the KDS can deliver keys. In reality, instead of having to request leaf keys, by using key hash tree, we can just let the client request higher level keys, like here. If you want to give the client access from key 2.0 to key 2.5, you should give it key 0.0 instead of all the lower level keys. So the client can effectively generate all the lower level keys by itself. So what we want to do is, in next benchmark, we want to shift the workload from server side to client side by letting the client request higher level keys like this. So next benchmark, the client requests all the highest level keys. Here, the KDS only needs to provide level 0 keys, and the whole key hash tree has to be generated as client side. By this, we can get a much faster block key generation speed than that of the key distribution speed. So here, the difference of the y-axis is, here is the key generation speed at the client side. It is not the key distribution speed because it covers the key distribution speed as well as the client-side key generation. We benchmarked key hash trees with various different widths and depths. So here the x-axis is the depth of the key hash tree, and y-axis shows how fast the client can generate block keys. In this first graph shows the result of using key hash tree with branching factor of 2. We begin with the depth of 2. The key hash tree is still very small, but it can already get more than 400,000 block keys generation per second. When the key hash tree depth goes to 3, we're getting even higher performance because the key hash tree is getting larger and cover more areas. By using one key, you can generate more block keys. However, with the trees getting deeper and deeper, the calculation overhead takes over and drags the performance down. So next one with branching factor 8, we see a range key now, a key hash tree can cover a much larger range, and the key processing speed increased greatly to about 1,400,000 keys per second. Now we also tested branching factor 4 and 6, and they lies within between. So the conclusion here is that the distribution speed of a key distribution server is about 140,000 queries per second, and the block key generation speed is about 700,000 per second because we use 2 KDSs. Now, in theory, this can support about 2.8 gigabytes per second in bandwidth. Well, this is good performance because you consider many HPC applications actually is not that I/O intensive. And also, same, if you want higher performance, you can just feel free to increase the number of key distribution servers or simply increase the size of the file system blocks. The paper has a good discussion on this topic. Also, it discusses what is the best way to choose the width and depth of the key hash tree. So next is the I/O performance by using 2 benchmarks. So this graph shows the results of the IOR test. It's an I/O intensive test. X-axis is the number of processes, Y-axis is the result I/O bandwidth of the IOR benchmark. So this first green line shows the raw write performance of the PVF2 file system we used. The blue line is AES encrypted write performance using the same key for all the data. So this is the upper bound of the performance we can get if you use encryption. The orange line shows Horus performance. Here, you can see the difference between the thick orange line and the blue line shows the overhead of Horus, which varies from 0.9% to 20%. For comparison, this green line shows the performance of traditional 1 key per block mode. As you can see, Horus is clearly much faster than the 1 key per block mode, which still offers the same flexibility of control. Excuse me, the last line is brown line. So another benchmark is the BTIO benchmark from NASA's parallel benchmarks. We use class C on 16 computer nodes. So here the green bar shows the raw performance without any encryption. Similarly, this brown bar shows the performance using encryption with the same key for all the data. So here, this test is not intensive as the previous IOR test, so the encryption overhead is not that big. But this one is also more like a real distributed application. And the orange bars also shows the performance horrors, and the performance loss here is about 5.9%. And for comparison, this is a result of using the traditional one key per block mode. Also, it has much higher overhead comparison with horrors. So the conclusion here, this is really a short talk. So yeah, the paper has a lot more detail than this. For example, the security analysis. Is this system really secure enough for the overhead here? So anyway, we can see Horus offers fine-grained security control that is especially important for large-scale storage systems running on HPC systems that handle secret or business secret projects. It can also be used with many different system models. It's easy to deploy, and also it's lightweight and performs relatively well under IO-intensive workloads. So that's it, and I'm happy to take your questions.
Mark Lobridge from HP Labs. So how do you revoke permission?
Well, that's a very good question. We have defined several ways. In the paper, we discuss one way. For example, you can actually use 2 root keys for a file. When you want to revoke some keys, you introduce a new root key and use that root key to generate a specific region of the file. And when you read the file, you can try which key works for that specific region. The paper has a somehow detailed discussion about that. Thanks.
Okay, Ben here from Virginia Commonwealth University. Very interesting work. Can you go back to one slide to show both range keys and block keys?
Sorry, which one?
Any slide to show both range keys and block keys.
Okay.
Oh, okay, so the question here is, it seems to me you assume those keys requested by users are perfectly grouped. How about if the keys requested by users are randomly scattered?
Well, generally, most of the HPC applications we have tested, actually, they require range data. So they just require this whole range of data. They don't do random read-write.
Not range data, those keys. So you assume those keys requested by users are perfectly grouped together, right? Mm-hmm. How about if the user requests keys, key 00, key 11, each key is of the left side of the lift keys.
Sorry, can you rephrase this question? I didn't quite understand, because normally
that means the keys requested user cannot be grouped together. They are scattered.
Oh, I know what you mean. So for many of the applications we have tested, they read and write in range. So it's consequence range. Right? Okay. So what you said is correct. If the read and write is totally random, scattered, it can be very hard. That's right.
My second question is, it seems to me so the depth of the tree could be very large. So if, for example, given the example from your example, if you need to generate 256 million keys, mm-hmm. then the depth of the tree could be as big as 28, if
yeah, actually,
so do you have any evaluation on the impact of overhead of the?
Well, actually, yeah. So the key hash tree doesn't have to be very deep. It only has to be very wide. And by wide, it only have to be wider at the first level. The paper have a good discussion about this. Actually, it have talked about the detail of how we did this with the key hash tree.
Okay. Gobelowski from Microsoft. Mm-hmm. If I understood what you said correctly, for your hash function, you used SHA-1 and you used AES-256 for the cipher. Mm-hmm. SHA-1 only generates 160 bits of output. Where did the other 90 bits of key come from?
Well, that's a very good question. So, to be honest, I can't remember exactly what we did. Maybe we repeated these bytes, I think. Yeah.
But aren't you using a keyed hash?
Yes, we use a keyed hash.
So you can generate different sizes?
Yeah, so, yeah, I think we use some trick to do this. Yeah, that's a very good question.
Why didn't
That's
you
the
use
implementation
SHA
detail.
256? That seems like the obvious thing to do. To use SHA 256, why didn't you do that?
Well, the purpose here is to study the properties of keyed hash tree. Choosing the hash function is freedom of the end user, actually.
Sure, but it affects your it'll affect your performance because it's a more expensive computation. But
Well, yeah, that's true. That's why we showed that. Yeah, that's true. But I believe using SHA1 or other functions have the similar. No, yeah, you're right. Yeah, it depends on the keyed hash tree.
Okay.
It's a hash function. Yeah, that's right.
Let's take just one more question, please.
Cyril Guyot, HGST. Given the keyed hash that you're using for generating the different node keys, if you need to, say, rekey one key sufficiently high in the tree, you basically have to re-encrypt everything that's children of that. Do you see that as a limitation, or?
Sorry, can you rephrase the question?
So if you change, if you want to rekey a key high up in the tree, if I understand the way you're derivating all the keys for the blocks that are children of this node, you'll have to basically regenerate everything.
What do you mean by rekey of the?
You want to change one key associated with a node. If
Well, that's true. As I said with Mark's question, we can just introduce one more root key. So each block will have two keys, and the client have the freedom to try these two keys to see which one works correctly.
Oh, I see.
Yeah.
Thank you.
I think it's similar to the key revocation problem.
Okay, let's thank our speakers one last time.
Thank you.